Okay. Oh, there we got it. Good morning, everyone, and welcome to this year's first breakfast seminar. I'm Eric Amlöv. I'm a PhD student here at the Integrated Transport Research Lab. We have these recurring breakfast seminars about once a month, covering wide topics of interest. Could be anything related to transport and new trends or new technology coming in general, but other broader subjects as well. I will ask you online to please keep your microphones muted and your cameras turned off during the presentation. The presentation will be about 30 or 40 minutes. If you'd like to ask questions, you can always post them in the chat. Just use the just write them in the chat, and then we'll get back to them once we have time for questions and discussion at the end. During the discussion, you can also use the raise hand feature, and then I will hand out the word to you when it's your time as well. If you have any technical issues at all, you can see on the bottom left corner an email to Erik Stenemo, my colleague, who could help you with any technical issues that might arise as well. I'll start by talking about the next seminar, because we have an upcoming seminar as well, which might be of interest to some of you as well, looking at the electrification of trucks and maybe the somewhat competitive, you could say, ideas of batteries as well. Could also be stationary charging and electric roads. So that's upcoming in about a month. So check out itrl.kth.se/events for more upcoming seminars as well. But moving on then to today's seminar with Anastasios and Manuel from the Division of Transport Planning here at KTH and from the Public Transport Administration here in Stockholm. They will talk about their master thesis that they did this last spring, talking about how you can design public transport networks using algorithms. A really interesting topic. They will speak for about 30 or 40 minutes, and then we will have time for questions in the end as well. And with that, I welcome Anastasios and Manuel to the floor.
Thank you, Erik. Yes, is it okay what we're showing in the Zoom meeting? Like you don't see
yeah, I can see it in the Zoom meeting. Okay. Let's turn off the microphone.
Was off. No. Weird.
Yeah.
Now, is it better now? Yes.
Yeah, okay.
Good. So
good morning, everyone. I would like to thank you for being here for today's presentation. With my colleague Manuel, we worked on the topic for the evaluation of bus networks by using an algorithm, and our case study was in Södertälje in Sweden. I'm Anastasios. I'm working at the Division of Transport Planning as a research engineer, as Eric mentioned before.
And my name is Manuel Chala. I'm a trainee in the Public Transport Administration in Stockholm.
Yeah, okay.
So first we wanted to start this presentation by describing what was the aim of our research. Basically, we have this algorithm that was designed for 2 previous students in their thesis. It was developed throughout 1 year. And then we received it to make an evaluation of the output of this one. The algorithm.
You can't see, can't see the presentation.
Yeah, we're seeing the presentation or the other slides. So. All good? Yep.
Yep.
Sorry about
Good.
that.
Thanks. So this algorithm tried to solve the urban transit routing problem, which in simple terms, it's the design of route sets based on a road network and a specific demand. For this evaluation of this algorithm, we use 2 types of assessment. The first one is a quantitative one. This is made by changing the different parameters in the algorithm. So we have a result for the objective in this algorithm. And the second one is a qualitative. We made some interviews with relevant stakeholders according to our case study, which we'll explain later. And as we said before, the main study area is the Södertälje greater area.
Now let's move on to a more theoretical background about the design of public transport networks. As you can imagine, the efficient design of public transport networks can offer multiple benefits to the society, to the economy, and to the environment, of course. The transit planning problem is a complex problem, and as you can see, the network design is one of the fundamental sub-problems, followed by the frequency setting, the development of the timetables, the bus scheduling, and the driver scheduling as well. In the literature, we found many papers that they use algorithms in order to design public transport networks. However, these algorithms are rarely being evaluated. And this is the main research gap that we try to bridge through our research.
So now going into details about our case study, like why Södertälje? This was chosen because it wasn't a big or a small city. It's a medium size. It has different companies there, like Scania and AstraZeneca. So it has some interesting transport behavior. It has both rural and urban areas. It's very close to Stockholm. And as it has all these different companies and still have residential, so the passenger demand is very significant. And finally, because it's reasonable separated from the rest of the network in the region, this means that as our study is only based for the bus network, not the tunnelbana, not the pendeltåg. The bus network is very isolated. It's only 2 networks who are connecting to Stockholm. The rest is between the area. And going a little bit into detail, so currently they have 20 bus routes operating. The average of the length is 17.2 kilometers. And in this network, we have around 7 nodes per route. This map is showing a little bit of the behavior, which I mentioned before. If we can see in the map that we have red dots and green dots. The reds are showing the origin of the trips and the green the destinations. So if we focus on the central area, we can see that the red dots are at the outskirts of the main Södertälje city, while the green ones are where the main bus stop station is and the pendeltåg stations are. So and also if we look at the suburbs or town around it, it's mainly red dots. So this means that as this map is showing the morning rush hour, it have the typical behavior where people live in the outskirts of the town and goes to the city center where to work or to commute to the main Stockholm. Yes, that was it.
Let's move on to the questions that we try to address and answer in our research. The first one is the presentation of the algorithm's output in a comprehensive way, since that's why we developed our own geovisualization strategy in order to achieve that. Moving on, we try to assess if the algorithm's output is feasible in a real-life scenario. And the third is, what do public transport planners think about the results? And that's why we had several meetings with people from the public transport administration here in Stockholm and from the public transport operator in Södertälje, Nobina. Let's move on to the methodology we followed in order to achieve our research output. First of all, we start with the literature review. We try to address the research gap. We try to see what other people did in the past. And we also had some meetings with the previous master thesis students that they developed the algorithms. And that helped us a lot to have a better understanding of the algorithm and how it performs. Then we moved to the exploration of the parameter by importing different input parameters, such as the number of transfers, the number of nodes, and the number of routes. And then we tried to visualize our results, understand the results, and select our best solutions. And we'll talk more later about that.
Yes, we continue this methodology with the geovisualization strategy, which is as we in the previous step we select the solutions that we want to present, and we have only an array of points and data. We need to visualize it in a map to make the easy to understand for the stakeholders in the next step. So we use QGIS and ArcGIS Online to make this geovisualization, and then we continue with the interviews, with a little feedback with the groups of interest. In this case was the operator Nobina, which is in charge of the Södertälje area. And we finalize with the research output. So according to all what we gather with this methodology to make some conclusions. Now we get a little bit technical here, as is an algorithm that we evaluated, but we want to focus on the core of this one. The core are the objective functions. The first one, this algorithm is trying to minimize these functions in order to improve the objective and the result of the network obtained. The first one is the passenger objective. This is simplified as an average travel time per passenger. This travel time includes the time in vehicle, and also if the connection between two nodes require a transfer, it's taken into account in this point. With this example, we also wanted to explain what this objective, what the passenger will like. So the best option for the passenger is if every node in the network is connected by one line. That's the best solution, which is of course not feasible from the operator side, which is then the next objective. This one is a little bit more simple. This is the total travel time for all the routes. So it's the summatory of the travel times. If we have a network like this, it will be the summatory of the time between all the links between nodes, and then all between the summatory of all the lines. This example also shows what would be the best for an operator, just to have one line that connects all the points and not multiple transport lines. So it will be more economically better for them. So with these two objectives, the next step is continue to represent it visually. We have a lot of solutions and a lot of scenarios, and this will be presented in the Pareto front.
Yeah, thanks, Manuel, for that. We use the Pareto front. As you maybe know, Pareto front is a fundamental concept in multi-objective optimization. The main concept describes the representation of the solutions that they have the best compromise between the two objectives. As you can see on the slide, yeah. Yeah. As you can see, the black dots in our graph represent the Pareto front efficient solutions that they have the best compromise between the two objectives. And as you can see, also we have a lot of other solutions when we're running the algorithm. The added value of this approach is that we can see the trade-off between the objectives for our current problem. And this can help and can facilitate decision making for the public transport operator, for example, and the public transport administration. Moving on, there are a lot of applications of the Pareto front in the transport field. For example, the first one, the mode choice problem, is one of the most important transport problems and has been a lot of undertaken research regarding the topic. In that problem, probably the conflicting objectives could be the cost, the speed, and environmental impact, for example. Moving on to the network design, about the cost, time, and accessibility. We also can move to the traffic management, which is also a hot topic in transport, including the travel time, the emissions emitted from different vehicle types, as well as the fuel consumption. Another type of problem is the fleet management, where, as you can imagine, the cost, the utilization of different type of vehicles could be contrasting objectives, as well as the public transport planning in general, with the inclusion of more than one public transport modes, including the cost, the travel time, and accessibility as potential conflicting objectives. And last, we can mention the parking management, which is a hot topic, especially for urban areas, where the cost, the accessibility, and sustainable rated indexes can be considered as potential conflicting objectives. But let's move on to our specific problem and how we made use of the Pareto front. As we described before, it's black dot describes a Pareto front efficient solution. One black dot describes, integrates the design of the whole network in Södertälje, as you can see, starting from the first route up to the last route. And in our X and Y axis are our two conflicting objectives, passenger and operator objective.
Yes. So we plan to make this evaluation by preparing different scenarios. These scenarios vary on the different parameters that it has as an input. In total, we created 18 scenarios, which is the combination between the number of roads, the maximum number of stops, and the terminal nodes. This is a group of nodes that were selected for the points to start or finish the routes there. So now all the nodes in the network. And we also have one scenario which included the current bus network as a starting point. So we wanted to check what happens when that's the case. Here we have a visualization of all the information we manage. First, this is to show like the quantity of data that was involved in this evaluation. In average, each scenario take around 2.5 days to perform. So because it did a maximum of 1,500 generations. If we focus first on this graph, this is one scenario from the 18 ones, not including the current bus network, just from starting with random designs of the bus network and start to optimize those lines. We can see that the creation of the Pareto front starts from here and then suddenly start to increase. Also, something important to show is this point here. This is the value that is obtained for the current, for both objective, the passenger and the operator, for the current bus network. So what we expected is that this algorithm had better results, and which happened when we included the current bus network. So as you can see, we obtain solutions inside that are lower for both objectives, for the passenger and the operator. So that are here.
Yeah, as you saw in the previous slide, we had a lot of solutions. So we tried to select some indicative ones in order to present to you. So from the first exploration of parameters scenarios, we selected these first two, and S1 and S2, as they had the closest objective values compared to the current situation. And then we have this final scenario that used as input the current bus network in Södertälje area. And as you can see, it performs a bit better compared to the current situation. Let's move on to the meetings we had with the different stakeholders, and mainly for the technical assessment of the routes with the Novina, the public transport operator. One important point that was highlighted during the first meeting about the scenarios 1 and 2 was the length of the routes. They mentioned about the European law that sets an upper threshold for as a limit for the maximum length of buses and other modes of public transport for passenger carriage. And as you can see in that solution, we have a route that its total length is about 92 kilometers. Moving on, we discussed about the appropriateness of the road network, which road segments can be used to facilitate the public transport vehicles. As you can see, what we discussed in the meeting, the specific segment from A to B, our design line follows this brown path. And as we were told, this is not appropriate for as a solution. And here you can see the current solution, the current bus line operates in Södertälje with the pink color. Another important point that was highlighted during our meetings was the shaft driving. Shaft driving is a special term in the public transport industry that refers to the diversion of the public transport vehicle from its original path to facilitate only one bus stop. For example, in that solution, the bus starts from the origin and, of course, ends to the destination. So for the facilitation of stop number 1, you can see a back and forth movement of the vehicle. So this is an example of shaft driving. Also, this example of the bus stop of the stop in the train station is also a great example of shaft driving. Another important point we discussed was about the fleet management and the different safety standards that apply to different kinds of routes, for example, the rural and the urban. And as we discussed, it's not possible to combine rural and urban parts in the same route, since different vehicles, different buses should be used for that. And here we have an example as a result from the algorithm that it actually does this combination. So this was an important point to be highlighted.
So we continue with the second meeting we have with Novina. In this one, we presented the final scenario, the one that was closest to the origin and have better objective values. The result for this one is presented in here. So we have almost half of the routes were a new design, 9 were short routes, and 4 existing ones. We go into detail with one of these groups. The first one are the short routes. As you can see in the map, they're mostly concentrated in near to the central bus station. What we interpret from these results is that the demand between the center of the city is very relevant, and it could be considered for the operator to create these short roads. Also increase the frequency of these ones. So because the demand apparently seems to require that, and we also see some examples here in ICVAR. Yeah. The next group are the existing roads. Here in this map, we are presenting 3 of those. So, for example, in this case, the current road is the green one, and the one that was designed for the algorithm is the red one. So, also the interpretation of these results are that these 4 routes should be important for the operation. Novena should be focused on these routes as the algorithm didn't modify. So it could mean that the design is good and should be also improved with headways. And the final group are the new designs. These are very interesting. Some of them are also improved solutions. We have one case here where I think was this green line, where the final, where Novena in one of these meetings commented that they were planning to do one of these changes in the road. So that was also very interesting for us to see that the algorithm actually is producing something that is going to be implemented in real life, which is the main focus of this research. And also the rest of them, it should be a proposal for them to evaluate and check if it's feasible to implement, comparing with the actual bus roads.
Yeah, now let's move on to the comparison of these 3 scenarios, S1 and S2, from the exploration of the parameters, with the final scenario in the current situation, which is visualized by the blue box plot here. As you can see, in terms of length, the first 2 box plots that they refer to the first 2 scenarios have a higher median in terms of length. However, the final scenario has a lower median of around 15 kilometers per route. And probably this is because of the existence of several short routes in that solution. However, according to the feedback we received, the existence of several short routes is not that viable for the public transport operator, since it decreases the breaks of the bus drivers. And now let's move on to the comparison in terms of travel time. As you can see, a similar trend applies here as well. The first 2 scenarios have a higher median in terms of travel time compared to the current situation, where the final scenario has an approximately similar median of travel time. Now we can move to the conclusions of our research. It was very interesting for us and exciting to explore how this algorithm performs and what was the feedback from the planners and from people working in the public transport administration. However, we believe that algorithms is just an auxiliary tool that can be used for the design. Of course, the local needs, we saw examples of the local public transport network. We also had some other regulations that needed to be followed. So the adjustment of the results in applicable real-life scenarios could be followed after the implementation of the algorithm. Another important thing is that probably the interpretation of the short routes, instead of just implementing them in a real-life scenario, could just imply a potential increase in the frequency, which is something that the operator and administration can be considered as well.
Yes, so another conclusion is that these routes that have a similar design implied an effective design from part of the operators, and that they should focus in keeping them and making them reliable for the passengers, so they can operate, because they are very important. And finally, this case for the route that is already being implemented by Novena, which we can say that the algorithm helps it could be a tool to help to the operators for the design of these new bus roads, or improving the actual ones.
Regarding some future research steps that we can propose is the modification of the objective functions, including other relevant factors as we mentioned before. However, what we understood from this whole journey into design of public transport networks was that the design itself needs to be combined with scheduling. So it would be very nice in the future to be combined with the urban transit scheduling problem. Another important thing is that specific road network requirements need to be considered when we design public transport networks, as we saw examples with inappropriate segments that were considered some routes.
Another future research could be the improvement of the computational time. As we mentioned before, it takes around 2.5 days for each scenario, which is it's important time. So one of the suggestions we make is also, because right now the algorithm use the Dijkstra shortest path. It could be a newer algorithm, that's the A star, or using a better machine for the implementation of this algorithm. And the final is the implementing this algorithm also with other case studies. Find another medium-sized cities that could be implemented, that can be improved this bus network, or also why not other modes of transportation, such as the boat here in the archipelago, or so on. So these are the references, and
would like to thank you for your attention, for people being here and for people online for your time.
Thank you so much.
Thank you.
Thank you, Manuel and Anastasios. Please, if you have any questions, just post them in the chat. Use the raise hand feature either here or manually for those of you who are here. But I'll just like to start by asking. So you showed this Pareto front with all of these different diagrams and so on, and so each dot is a separate solution.
Exactly.
Is that so? There's a lot of different. So that's like a complete network. It's not
exactly.
One,
it's a complete network.
It's not one single route.
No.
Oh, so there's like a lot of different.
Yeah, and in the graph, the more dynamic we had here, it's more obvious how many solutions we had and how many we had to evaluate and select. For further evaluation. Thanks for pointing this out.
And I guess that's which one to choose is a bit hard, and that's why you're using the Pareto front to sort of see at least the best solutions to evaluate, I guess.
Yes, actually, for that point, because it's a little bit in detail, we use a specific methodology, which is the Nash solution. That consider the values, the minimum values and the maximum, and different points in the Pareto front. So we can choose the actual optimal one, because it's really different. We have so many solutions, as you mentioned. Each point is a whole set of routes, so that was very critical for our investigation.
And I guess that's the points on like either end of the spectrum, either really high or really to the right, are like really good at some aspects, but pretty terrible at the other aspect, I would assume.
And this is a challenge of multi-objective optimization, right? You need to find this best trade-off between the objectives.
For example, if we go a little bit in this,
are you maybe sharing the screen? Yes.
Okay,
awesome.
But what I wanted to say is that the values in the, for example, here in the limit are very good for the operator as has a low value, but it's really high for the passenger. So it's not that set of routes wouldn't be a good solution. So what we have tried to find is a compromise between both objective. So we use the Nash selection for that.
Interesting. So, what was the what's the feedback that you've gotten from Naveen and the public transport administration? Did they think that this was interesting, or what's the I mean, you described that some of the solutions of your final solution is like existing routes. Some are really short, so probably not interesting in themselves, and others are different in some way. Well, what's been the feedback?
Yeah, apart from the points that we discussed in the presentation regarding the length and the appropriateness of the road network, we received some feedback, as Manuel mentioned. Some changes that the algorithm proposed were actually been thinking from the public transport operator to be implemented. So for us, that was really interesting.
Oh, so the solutions were already like thought out.
Exactly.
Okay, but then you kind of confirm that this is probably a good solution.
And they were also people in Nobina are really excited about that, because it was like seeing about the future. Yeah, so I think we had a balanced feedback, like pointing out the point that should be considered in the next steps, but also check that the algorithm has actually potential of being implemented in some output, in some feasible output.
Yeah. Interesting. A question, can you please come up here so that the people online can hear as well? It's always nice to see you as well.
I hope you can hear me online as well. Thank you for the presentation. Whether I understood correctly, the input was traveled, today's travel, like today's travel patterns in some way.
Yes.
You have a certain amount of people who travel public transport, so it's not made for potential new passengers, but it's optimized for those who travel already today by bus, I assume.
Yes, the input that we use is current demand and the travel time between the calculated travel time between the nodes. But if the demand somehow can be modified to include, for example, a new residential area, it could be it could be modified as the demand input, the matrix that we use. So it could be work for that too.
Okay, thank you.
So you could use number of car trips in a for a network as well, and generate this is the best network for car users if you want to attract car users as well.
Yeah, exactly.
Interesting. You mentioned at the end in the conclusion that there would be other potential regarding the objective function, where in this case you're minimizing the travel time for passengers, for example. You also mentioned that there could be other potential factors that you want to include as well. Can you mention any of these factors that you think are interesting to include in the future?
I don't know, maybe accessibility index or indexes, environmental related indexes for the public transport vehicles. That would be also nice, since environment is a really hot topic as well with the transport.
Yes, I think that was one of the most important one. Of course, it's hard because to get the information about that, but it really will come with a better output of this algorithm. We include such as accessibility.
Interesting. A question in the room.
The physical raise hand feature. Actually, I have two questions. I'll raise both hands. So the first one connects to the demand. Clearly, what you are investigating is using static demand, people that are, and the further away you get from the current situation, the more unlikely it is. For instance, the further away you go towards the solutions with really bad passenger performance, not many people will still be going and taking the bus. And the other way around, if you propose a completely new routing system, you maybe become interesting for a lot of other. And then connected to that, did you investigate, for instance, of all the points that look to be, better? What is the difference in terms of minimum amount of changes from the current network? So which of all those solutions that are potentially better would be the most attractive from a minimum amount of changes point of view?
Oh. I mean, you mean minimum amount of changes in the
For
current?
the operator, yeah. So for
okay,
Nobina,
okay.
I'm like, okay, I only
Okay.
have to do this, and then I'm, 1% better, which is great.
We didn't.
That's nice.
Yeah,
That's a nice question, actually. And
yeah, we select the final scenario that we presented. It was based on the distance that we have to it was the biggest distance from the current situation. So it was the optimal in terms of this both objective,
Yeah.
But not in terms of the changes that the operator will have to do. So that will be an interesting future step for this research.
however, I need to add that in this final scenario, almost half of the proposed routes are similar or the implied potential frequency increase.
Yeah.
So yeah.
Yeah, I think we consider it's still a
that's
very
a
good
nice
solution,
point,
but yeah,
Gustavo,
we didn't check all of them because there were actually a lot, but it could be an interesting.
But you looked at having a less amount of routes as well.
Yeah.
So could be a simplification of the network, I guess, as well. Did you have any more questions?
No, that was great. That
Okay.
was my combined.
No.
It was a combined question. So I'll ask a bit. Did you look at any differences between, for example, weekdays and weekends, where you can kind of imagine that there's other travel patterns? Did you have any look at this in your work?
No, the demand that we have was for the morning rush hour, as it came from like the previous investigation, previous research that was done. So yeah, which is also like as a transport planner do, designed for the critical situation. So that we focus on the rush hour in the morning.
Yeah.
But I mean, you could definitely imagine that there's other demand for other types of networks or more cheaper networks, I guess, in the weekends as well. We don't have the same. I mean, you kind of use that with different frequencies, I guess, on lines as well, that you have all the same lines during the weekends, but some of them run only, what do I know, once every hour instead of once every 15 minutes. That's maybe during the rush hour and then weekend, for example, I guess. But I mean, it is possible to have a look at.
Absolutely.
Okay.
Yeah, it depends of getting, of course, the information. It's mainly because of that, but absolutely, the algorithm works. Could work with the data.
Do you have any questions online? No, I don't think so.
Oh no, I can keep on going.
Go on.
I'm just wondering, this is speculating. It's not supposed to be part of your work, but would there be a way in which you could use this algorithm or extend it to figure out which parts are not worth serving with a classical bus route, and maybe with something like DRT in connection? Like, would it be possible to extend this to say, okay, you know what, from here on, you can't really defend this, this last part, but we could maybe do it. Would it be possible? It's just plain speculation, but
like the algorithm, of course, it's available to make all types of modification we want, but and added some restrictions. So it would depend on how specific we would like to make this.
I mean, I was thinking, but I'm thinking, could we, like, if you do it in 2 steps, first figure out, like, putting some cutoff, say, figuring out like which passengers are, above a cutoff, like too far away to serve reasonably, and then look for, okay, what alternative solution could you give them? I'm just wondering. I'm just thinking out aloud. It would be interesting. I don't think we're going to solve it right now, but
yeah. Well, but we actually have in the actual network, we have really like a suburb which was really far away, and the algorithm, which is based on the demand, it only created one route to that point, which is the minimum to connect that node to the
Yeah.
city center, the main destination point.
That would be also interesting because we have this restriction with the different vehicle types that need to be used for urban and rural. Urban and rural, yeah.
Yep.
So this could imply probably a potential change in the mode. Instead of having a transfer in a station, for example.
Yeah. So,
But yeah,
in principle, it could be then. Yeah.
Yeah.
Thank you. Super
thank you,
interesting.
thank you. Yeah, thank you.
Okay. Do we have any other questions in the room or online, maybe? No, it doesn't seem so. Then I would like to thank Anastasios and Manuel for giving this talk. It's a really interesting subject, I think. So thank you for coming here and presenting, and thank you all of those of you who joined online or here as well. For those physically here, please stick around if you want to if you have any specific questions for Manuel and Anastasios now afterwards as well. And otherwise, I hope that I will see you on the next webinar we have on electrification of trucks in Sweden. Please check out our website if you want to know anything more or sign up for that seminar. Thank you.
Thank you.
Thank you so much.